about this. This way, I do a lot of my recordings at home. Okay, so this is where our concept of the interval of convergence comes in. It consists of all values of x for which certain series converges. The radius of convergence is half of the length of the interval of convergence. For example, in our previous example, the interval of convergence was -1 is less than x, which is less than 1. Okay, and the radius of convergence is 1. It's half the interval. Now, I can show you this graphically, and it will actually make more sense. -1, 1, 0. So that's our interval, is -1 to 1. But you can draw a circle, and there's our radius. It just goes around. But it's actually just between there and there. That's our interval. And remember, that's an open interval. Okay? In this work, we're going to ignore the issue of convergence at endpoints. That means we're going to talk about the open interval of convergence because that's not included there. It's important to be able to find the intervals of convergence, specifically for power series, because your power series is only valid on the interval of convergence. Finding intervals of convergence of power series. 1. Find an expression that an plus 1, or ak plus 1 if you want k's, over an converges to, and this expression will probably be a function of x, say fx. And I'm going to show you a few examples so you can see this. Solve to get fx is less than 1. So that's where it will converge. And then you'll get minus r is less than x, which is less than r, or you'll have minus r is less than x minus c, if we're actually about c, which is less than r, and r is going to be your radius of convergence. Your interval on convergence, on the other hand, in this case it's from minus r to r, but in this case we have to add our c, so we get minus r plus c to r plus c. Note, if fx is less than 1 for all values of x, then your interval of convergence is minus infinity to infinity, which is basically all x. So it's valid for all x. If fx is less than 1 only for x equals to 0, then your interval of convergence is just 0. Okay, so let's do 3 examples, and that will end the topic. Right. Find the open interval of convergence and radius of convergence for the series x to the 2n over 9n. If we expand this out a little bit, we'll have 1 plus, so that's just going x to the 0 is going to be 1, 9 to the 0 is 1. So x squared when n is equal to 1 over 9 plus x4 over 81, etc. And if we look at this, this is in fact a geometric sequence. Well, it's a series here. The way we've written it is a series, but the actual little terms are geometric. With common ratio x squared over 9, which you can see if you do that divided, this one here divided by this one, we'll get x squared over 9, and that divided by this one, we'll get x squared over 9. Now, it converges when our common factor, or common ratio, is less than 1. So that means we have x squared over 9 is less than 1. X squared is less than 1. 9. Which goes to minus 3 is less than x, which is less than 3. Now this is the open interval of convergence. Okay. What's our radius of convergence? Anyone? Three? Yep. 3. So we've got example 2. Find the open interval of convergence and radius of convergence for this series. If we expand this out a little bit, we have n equals to 0 to infinity of x minus 5 to the n. We have, now it's from 0, so we'll have 1 plus x minus 5 over 4 plus x minus 5 to the power of 2 over 16 plus etc. Now by inspection, the common ratio is again x minus 5 over 4. Okay, so when r is less than 1, it converges. So as an aside, we have x minus 5 over 4 is less than 1. Now 4 doesn't change. So we have x minus 5 less than 4. So we've got minus 4 is less than x minus 5. So this one we have that c, which means our interval of convergence, we're going to add 5 to each side. 1 is less than x, which is less than 9. That's our interval of convergence, or open interval of convergence. Now, I can put this on a number line. I won't do circle. Now, that goes from here. Oh, sorry, no, it doesn't go from there, does it? Sorry about leading you down the garden track. It goes from here to here. Which means halfway, that's our radius of convergence. You could also do this numerically. 9 minus 1 divided by 2 is equal to 4. Okay? Any questions? Okay. One last question. Find the open interval of convergence and radius of convergence for the series. Now, this series here is e to the x. This is e to the x. And you can see that you can actually find a relationship to express it. So for the open interval of convergence, for convergence, we need, now this is where we follow those instructions, the limit of n goes to infinity of a n plus 1 over a to the n is less than 1. So, looking at ours, we have limit n goes to infinity of x n plus 1 over n plus 1 factorial. Now, when you're dividing by a fraction, so this is actually going to be dividing by a fraction, you actually multiply by the inverse of that fraction. We have that. And this can be expanded out. So we'll have x to the n times by n over n factorial times by n plus 1, because that's just the next number, n factorial, over x to the n, which means that we can cancel here common factors, and we'll be left with limit don't need there. Limit of n equals n goes to infinity of x over n plus 1. We can bring that x out the front because n is going to infinity. And you can see if I make n go to infinity, what will I get as my result? Zero. So we'll actually have times by 0. Let me just write that so it's a little bit bigger. Which is equal to 0. And this happens for all x. So that means the limiting value in this case is 0, always less than 1 for all x. So the interval of convergence, is, what do you think? It's always x less than 1. No matter what x values there are, this thing's equal to 0. So the interval of convergence is going to be for this particular series exactly negative infinity to infinity. So all values of x. And that completes the course for this semester, spring 2017. I'm sure people are cheering you, or you're going to miss it. Okay.